Great, thanks very much, and thanks for the invitation to come and talk. I know it's getting very late, so hopefully I'll keep you entertained for the next 35, 40 minutes. But what I want to do now is look at a different framework for the whole topic of negative emissions, and indeed for the whole topic of climate change itself. And the idea is to put all of this into an Earth system perspective. Notice we use singular, Earth system, and that's looking at our planetary system as a single system, including all of us humans and our institutions' activities, as well as the geophysics, the biosphere, and so on. So 3 parts to my talk. The first will be fairly short, just in the way of background. First of all, the Earth as a complex system. Second, this concept of the Anthropocene. Where is the Earth system going? And then we'll look at future trajectories of the Earth system, and that's where negative emission technologies, CDR, come into the picture quite strongly. And I'm going to take a long-term perspective because I want to cover the entire time period that humans have been on the planet. So this data here that I'll look at in more detail in a moment goes back to over 400,000 years. So if we look at this data in more detail, this is ice core data from Antarctica. So it's got 3 parameters: carbon dioxide, methane, and temperature. And the patterns are really what's important here, and that's very good evidence that we're looking at a single complex system. So we talk about this in complex system theory in terms of limit cycles. So if we look at CO2, notice that the lower bound and the upper bound are pretty much the same through that cyclical pattern. Same thing for methane, same thing for CO2. And notice that the cycles are pretty much of the same length. Now, obviously, just from looking at this, you can say there must be a relationship between these 3, CO2, temperature, and methane. And indeed, there is. But it's not a simple cause-effect relationship. It's much more complex than that. I won't go into it, but there's been an awful lot written about how the Earth system actually works. So that's our basis. Complex system scientists like to put these limit cycles in a diagram like this, where the axes now are sea level on the horizontal axis and temperature on the vertical axis. And these cycles operate on about a periodicity of 100,000 years, oscillating between, at the bottom, here you see low temperature, low sea level, oscillating to the short interglacials of high temperature, high sea levels. Temperature leads sea level, and that's because of the lag times in the gain or loss of ice in the Earth system. So if we now look at this in more detail, as I said before, this encompasses the entire time that humans, fully modern humans, have been on the planet. We've been through 2 of these glacial, interglacial cycles. But this last interglacial here is particularly important. It's a little bit longer than the ones before it, and it's a little bit cooler than the ones before it. It's called the Holocene, and it's important because that's allowed humans to begin to develop agriculture, then settlements, then cities, then more complex civilizations, and so on. So if we look at the last 100,000 years in a little bit more detail, it looks like this. So you can see the period before this, and by the way, Australia's been inhabited since about this period here, 65,000 years. So indigenous Australians had a really rough go in terms of a much more variable climate, much colder climate, much more erratic climate, rapid rise out of the Ice Age, and then we have a relatively stable period of nearly 12,000 years, which is called the Holocene. Now, obviously, this is changing very rapidly. So if we look at the last 250 years of that 12,000 years, you see, first of all, CO2 emissions from human activities are going up remarkably rapidly, really from the middle of the 20th century. And not surprisingly, because we know there's a good relationship between CO2 and climate, temperature has been going up too. Again, pretty strongly since about the middle of the 20th century. So that's pretty well known. But we can put this again in a broader human perspective too by looking at the 1750 to 2010 period. And looking at a number of indicators that we tried to put together to say, if you needed to describe us humans, our activities, in a set of 12 indicators, what would you do? Well, you have population, you have economy, you have energy, you have urbanization, and you have resource use and communication and connections. And so when you put all this data together, you find, again, remarkably, around 1950, the human part of the Earth system took off in terms of numbers, economy, resource use, activity, and so on. Well, that's quite interesting in its own right, but of course our interest as Earth system scientists is to say, Well, has this had any demonstrable effect on the Earth system, the rest of the Earth system? And the answer is yes. So the top 6 of these 12 are the geosphere, atmosphere, ocean, climate. The bottom 6 are the biosphere, the living part of the planet, again from the year 1750 to 2010. And again, you can see some quite remarkable changes. And the patterns here are a little bit different because there are lags built into the geobiophysical part of the Earth system. But 2 things stand out here. In every case, after about the middle of the 20th century, these parameters are moving outside of Holocene norms. And we know that with a high degree of certainty. And the second thing is we know this is not natural variability. In each of these cases, we have very strong evidence that the primary driver for these changes are human activities, not natural variability in the system. So this sort of data, we're putting this together as part of the International Geosphere Biosphere Program. And one of our co-chairs, this gentleman, Paul Crutzen, looking at data like this said, you know, guys, we're not in the Holocene anymore. And he blurted out the word in a 2000 meeting, we're in the Anthropocene. And so that's where the term Anthropocene came from, and it had a very specific meaning. It had a 2-fold meaning. One is an Earth system meaning, the fact that we had left the Holocene, that nearly 12,000-year period of stability, and we're now entering into a period of rapid trajectory away from it. And the second was a geological one, where he posed the question to the geologists saying, you should consider that we have geologically, stratigraphically left the Holocene, and we should be in a new, and he proposed it at the epochal level, we should be in a new epoch, which he called the Anthropocene. I'll talk mainly about the climate, but I don't want to forget about the biosphere, because that's also very important. We'll see later on why it's really important in terms of the climate as well. But just very briefly, what are humans doing to the biosphere? Well, we're now starting to direct evolution in many different ways. Here's the Anthropocene chicken, 5 times bigger in biomass than the chook that I knew when I grew up in the 1950s. Directed evolution. We now totally dominate terrestrial vertebrate biomass. These are creatures living on land that have a backbone. 97% of the mass is just us, our body weight and our domesticates. All wild mammals, amphibians, reptiles, and birds are less than 3% of the biomass. So we humans absolutely dominate land systems. And of course, we're heading for a mass extinction event. Extinction or threatened rates for all of these different types of biological species are increasing. The current extinction rates are 10 to 100 times higher than the background level, and we're probably headed for the 6th great extinction in Earth history in probably 2 or 3 human lifetimes, given present trajectories. So massive changes to the biosphere. But now let me go back to the climate, because this is really what we're talking about here in terms of negative emission technologies, meeting the Paris targets, and so on. So that's the contemporary change in global average temperature. But again, from an Earth system perspective, we need to put this in a much longer time frame. So here I've taken a 2,000-year temperature proxy record. This goes back to the Roman Empire, AD 0. And you can see natural variability here, but within a pretty narrow band of variability. Very, very slight cooling trend in the last 2,000 years. But the contemporary temperature change that we've observed over the last 100 years or so is now marked here on the end of this. This is the human influence on the climate system. So you see it's quite dramatic compared to what's happened the last 2,000 years. Rates of change are really important. For the last half century, since 1970, the global average temperature is rising about 170 times the background rate over the past 7,000 years. That's why the biosphere is having real trouble keeping up with this. Rate of atmospheric CO2 increase over the past 2 decades is about 100 times the maximum rate, sustained rate, during the last deglaciation, the last time CO2 rose very rapidly. Rates of increase in ocean acidification is unparalleled for probably the last 300 million years. That goes through quite a few different geological time intervals. So that sort of evidence prompted a group of 16 of us to look at the Earth system, or look at the climate problem and the biosphere problem in a new framework. And that is looking again at the Earth as a single system, looking at the Anthropocene, and then asking ourselves, using that framework, where might we be going in the future? So the first thing we said is this is the common narrative in terms of climate. You have various emission scenarios for the future, and then you can use climate models to assess what the temperature might do. The point being here that out to 2100, the dominant driver of where the temperature is going are human emissions of CO2. And we asked ourselves the question of looking at the Earth system and looking at its longer history, is this really an accurate representation of how the Earth system operates? So we wanted to explore that in more detail. Now, more recently, we've just had this report from the IPCC of a 1.5 degree target, what's entailed in meeting that target. And this becomes relevant, too, when we've cast this in a broader term perspective. I think several people have mentioned the carbon budget as one way of assessing how much more we can emit for a given temperature target. This comes directly from table 2.2 in the 1.5 report. 50% probability, 66% probability. These are now gigatons of carbon, and this, by the way, should also be gigatons of carbon, not CO2. But you see that the uncertainties here are of about the same order of magnitude as the budget itself, which means we're getting really close to exhausting these budgets. If you add up all the uncertainties, one of which is skewed toward reducing the budget, and the one Earth system feedback, only one put in here, permafrost, you see that you should reduce this budget by about 55 billion tons. And that takes the 66% probability down to about 10 years. I think Mark mentioned that just now. About 10 years of emissions at current rates. So what about CDR in these 1.5 degree pathways? All of them use CDR to some extent. We noticed, several people have noted, CDR deployed at scale is unproven, at least at the present, and reliance on it at scale is still a major risk. And of course, the longer we delay reducing emissions, the more we have to rely on it. These are some of the emission reduction trajectories in the SR 1.5. All of them have CDR to some extent. And the longer we delay, the more we emit, of course, the more you have to rely upon it. The other point that comes out is that there is a real risk, of course, that we will have overshoot, that we may miss the 1.5 and then have to try to bring the temperature back down later in the century. I'll return to that a little bit later. So getting back to the Earth system perspective, trying to put this in that Earth system perspective, here's our limit cycle here. Here's where we think the Earth is today, between points A and B. And there's pretty good evidence we've broken out of that cycle. Even if we could get emissions to zero tomorrow, we would not go back into a glaciation. We've already missed that. So we are committed to the next 100,000 years of being in a much warmer temperature than the Earth system would normally do. The question now is, as we're going up this trajectory toward what we call hothouse Earth, how can we possibly avoid that? And of course, this is the aim of the SR 1.5, and indeed the IPCC reports, is to give us some advice on how we can get into what we call a stabilized Earth trajectory. These letters here refer to time intervals in Earth's past that could be achievable or accessible on our current trajectory. This comes from our paper. You can see what they are. Going further back in time, temperature is getting hotter and hotter. Sea level is getting more and more, sea level rise. But the interesting thing is the atmospheric CO2 concentrations. Mid-Holocene was about 260, Eemian 280 to 300. The mid-Pliocene is probably what we're committed to now if you look at our CO2. Last time CO2 was 400 was 3 to 4 million years ago. Temperature eventually stabilized then at 2 to 3. Sea level was 10 to 22 meters higher than pre-industrial. And of course, if we keep on emitting CO2 up toward 500 or above, mid-Miocene conditions may be reached, 4 or 5 degrees. That's the high emissions IPCC scenarios. But sea levels were anywhere from 10 to 60 meters higher back then. So again, let's go back here. Now, if we put the IPCC projections on a 2,000-year time frame, they look like this. So here's the low emissions RCP 2.6. Here's RCP 8.5. Notice what a tremendously steep and rapid temperature change that is compared to more geological timescales. So it's really important that we look at it this way because this is what the biosphere has to cope with. And this is what a lot of the inbuilt resilience of the Earth system in terms of biospheric feedbacks, that's what it has to cope with. So there's what our committed is, probably between 1.5 and 2. And the high emissions one is somewhere between 4 and 5, which will be a really severe challenge to contemporary civilization. And of course, the intermediate trajectories give you temperature rises between 2, 3, 3, and 4. And you see a lot of people saying, well, our NDCs will give us somewhere around 3. But our analysis says that if you look at feedbacks and tipping points in the Earth system, this whole range may be inaccessible. That once you start knocking over these feedbacks, the Earth system itself will want to go to a hotter, more stable state that it's been in many times in the past. So let's look a bit more now at this. What are some of these feedbacks? Well, some are involved in ice albedo. Don't have time to go into that. I want to focus on the biospheric ones. Permafrost thawing is included, permafrost thawing is included in the SR 1.5 report, but there's a whole host which are not. One is weakening of land and ocean physiological sinks, marine bacterial respiration, and forest dieback in the Amazon and Boreal. And we've made estimates at 2 degrees and 1.5 degree forcing of how big those are. The bottom line is you could wipe out the entire SR 1.5 budgets by these feedbacks. And you can wipe out a fair bit of the 2 degree forcings by these feedbacks. Again, our argument here is that these intermediate temperature ranges may be inaccessible as these feedbacks get going. So there's been an analysis, actually several of them, many of them coming from the Potsdam Institute in Germany and collaborators, on what these feedbacks look like. And here's a good map of them. But really 3 different types of these tipping elements. I've been talking a little bit mainly about the biospheric ones here in green. But of course, melting of ice is really important, particularly at the poles, but also in some of the big continental glaciers. And circulation change is also important in terms of atmospheric circulation and in terms of oceanic circulation and in terms of coupled ocean-atmosphere circulation. We can see that at 1 degree warming, where we are today, some of these are already being destabilized. The Amazon basin, for example, has basically become carbon neutral with serious droughts in 2005, 2010, and another one in 2015-16, which is wiping out a couple decades of carbon storage. We can look at the permafrost up in Siberia. That's starting to bubble out, fortunately still at low rates, but the IPCC estimates that anywhere from 50 to 250 billion tons could be lost by 2100, depending on the forcing it sees. Arctic sea ice, we've probably crossed the tipping point for that already, and we're probably committed to having an ice-free summertime Arctic in the next decade or 2, which will increase the warming quite significantly in the northern hemisphere. Coral reefs, we may have crossed that tipping point already as well. Greenland, that is losing ice at an increasing rate. Tipping point could lie as low as 1.5 or 2 degrees for that. Antarctica, the west is losing ice also at an increasing rate, and that's mainly marine-based ice sheets that are losing ice through erosion from warmer seawater. So if you put these various tipping elements on a temperature graph, you can sort of classify them into what temperatures they are likely to be tipped. So this is the Holocene here, the last nearly 12,000 years. Here's the human-driven temperature spike at the end. Here's the Paris range from 1.5 to 2. And here are the RCPs where they might take us in 2100. So here are the ones that could be tipping elements that could be tipped in the Paris range. Here are ones that would take higher degrees of forcing to tip. But most of these are polar ice, interestingly, West Antarctic, Greenland, Arctic summer sea ice, and alpine glaciers, but also coral reefs. Now, the interesting things, that although we've put these here as individual tipping elements, of course, the Earth being a single system, these are linked. So this is some recent work done by Jonathan Dongas and Ricardo Winkelmann at PIC, who have put these together in a tipping cascades map. And this sort of gives you the system approach to how these could act together to build a planetary threshold. So the idea is that these light yellow ones could be tipped in a 1 to 3 degree temperature range, i.e. where we are now or where we're going over the next couple of decades. And there you see the polar ice sheets, and here you see coral reefs and alpine glaciers. But there's a number of important ones at 3 to 5 that could be tipped. So those are in the range of the NDCs, and they're in the range of the additional warming if you tip the 1 to 3. So you start these like a pack of dominoes. You start tipping the first dominoes, they tip more, and you end up tipping most of these. So this is a hypothesis that how you get from individual tipping elements to a planetary threshold. We tried to put all this together in one hopefully easier to understand diagram than those limit cycle diagrams are. It's called a stability landscape. And what it's doing here is looking at sort of valleys, ridges, and so on, and looking at where the Earth system would like to sit naturally. In other words, where are stable states of the Earth system, given its internal dynamics with external forcing. And here's our glacial interglacial limit cycle. So here's a glacial state. Here, it's color blue, much colder, very stable state when it's in it. And about every 100,000 years, the Earth's orbital parameters trigger feedbacks which shove the Earth system up into a small temporary valley high above the glacial stage, where it sits anywhere for 5 to 10,000 years. This is the Holocene, most recent one. And that's eroded away, again, by the Earth's orbital parameters, feedbacks, and it slides back down and spends the better part of 100,000 years here. But our own forcing of the system, particularly since the mid-1950s, has pushed the Earth out of this glacial interglacial cycle into something new, something that's starting to emerge, which is another valley that is moving toward a very stable state, but it's much hotter. So we're sitting here outside of the glacial interglacial limit cycle. If we simply took off the human pressure now, the Earth would rattle around in here and not get back to a glacial state. But the question is, this valley is steepening, and how close are we to a point of no return where the Earth is simply going to slide down this deepening valley across a waterfall or a cliff into hothouse Earth, where it would sit for millions of years because it's an extremely stable condition of the Earth system. And what is it going to take, we call it Earth system stewardship, to move the Earth into a human-created valley, stabilized Earth, and park it there and keep it there? This is where negative emission technologies, CDR, come in. They are and they will be required to move the Earth system across, out of this emerging valley of a hotter conditions into what we call a stabilized Earth. Still warmer than the Holocene, but one that would avoid hothouse Earth. So that's really the framework we're putting together when you look at the Earth system from a complex systems point of view. Now, the interesting point here is the planetary threshold. Just put what we're talking about here. This glacial interglacial cycling that you see here from the Vostok ice core, that is this deep blue valley. Here it is at lower temperatures. Earth spends much of its time here. It comes out rapidly into this little temporary stability domain, and then it's pulled back down here for most of the time. Complex system scientists actually call this a pullback attractor rather than a limit cycle. That's the more appropriate name. Here, this temperature spike, this is where we are now. We've pushed the Earth system out of this limit cycle, and we're sitting here. Here is our tipping point cascade. That creates what we call here a planetary threshold. The question is, when we start this, how far can we go before we can't get back? In other words, where are the dominoes going to keep falling, even if we take all the pressure off the Earth system? We don't know where that lies, but it lies above this threshold. And so a really good analogy you can think of is a boat approaching a waterfall. Is that, of course, once it gets down in here, it's going to go over. There is some point at which you can't turn the boat around because the current is increasing and taking the boat down. We don't know where that is, and that's really where the risk analysis needs to be, is how far down this pathway toward hothouse Earth can we go? Where is 1.5? Where is 2? We don't know exactly where they lie with respect to this tipping cascade. But we're pretty sure that there's somewhere between 1.5 and 3 where you're probably going to get sucked down this pathway into a very stable state of the Earth system. So hothouse Earth, if we actually go there 4 or 5 degrees warmer, is it even inhabitable? Well, here's the best we could discern from the literature. Most of the tropics and subtropics will be too hot for human habitation. We'll have to move back toward the poles. Changing temperature and rainfall patterns will likely make some of the current large agricultural zones, central USA, northeast China, for example, unproductive. So we would have to move most of our agricultural production to different areas on the planet. Sea level rise of 20 to 40 meters is ultimately likely in hothouse Earth, drowning coastal cities, agricultural areas, and infrastructure. The issue here, of course, is the rate. And again, looking at the literature, we think the maximum rate may be 2 meters a century, because we've seen that in the past when the Earth has moved rapidly into much hotter conditions. And there's been one estimate of the maximum carrying capacity of a hothouse Earth of about 1 billion humans. It wouldn't wipe humans out, but it would reduce our population from current population about 7.5 to 1. Now you might ask, how plausible is this scenario? And we asked that ourselves in our paper. And here is some circumstantial evidence to say that you should at least not dismiss this scenario out of hand. First of all, there is absolutely no doubt about the complex system behavior of the Earth system in the late Quaternary, particularly over the last 1.2 million years. That's without question how it behaves. It oscillates between these two states, glacial and interglacial. Hothouse Earth conditions are accessible with projected CO2 concentration and temperature later this century. So if you look at the IPCC high emission scenarios, they give you hothouse Earth conditions by 2100. And if we're right, even intermediate temperature rises plus feedbacks will get you to those same conditions. What about those feedback processes that we put in that cascades diagram? Well, some of these we know for certain operate because they're the same ones that have operated in the glacial and interglacial cycling. For example, outgassing of CO2 from oceans as they warm, waxing and waning of ice sheets and changes in albedo. So we know those operate, and we can actually measure how important they are during glacial and interglacial cycling. And as I mentioned, observations show some tipping elements are vulnerable at 1 to 3 degree temperature rise. So we're seeing some of them being destabilized today. So going back to the 1.5 special report, what does our analysis, what would our analysis say about that? So go back to our carbon budget for the 1.5 degree C. Again, sorry, this is a typo. This should be gigaton C, not gigaton CO2. And here we have the net uncertainty feedback effect according to the IPCC of minus 55, which is actually already very important, particularly for the 66% probability. So if we add on our additional feedbacks, which are not yet in the Earth system models, and they're not in there yet because we don't know enough about them quantitatively to be able to put them in the models. Other biome tipping elements, by that we mean Amazon boreal forest and so on, will take another 40 billion tons off that budget. Weakening of land and ocean carbon sinks. This is actually being observed, and it is in IPCC AR5, but offline. Some Earth system models can actually simulate these. And they simulate about 100 billion tons off that budget for a 1.5 degree temperature rise by 2100. We're not certain yet whether they're actually included in the IPCC carbon budgets. Our analysis, looking at the individual model runs, says they are not. And if they are not, that's another additional one. So when you add all this together, you have to take nearly 200 billion tons off the 1.5 budgets. And they eliminate the 66% probability and basically eliminate the 50% probability. These are estimates of feedback strength at a forcing of 1.5, based on the literature as we know it today. So basically what we're saying, if our analysis is correct, we're running a risk of the fact that we're already committed to 1.5, and at 1.5 we're running a risk that we may be starting a tipping point cascade. Overshoot scenarios, what does it say about that? I think this may have already been mentioned in this meeting, is that the difference of 0.2 or 0.3 of a degree may be really, really important, because it's possible that if we could cap warming to 1.5, we certainly could raise the temperature a little bit more than that through these feedbacks, but perhaps we could avoid the cascade. We don't know for sure where that tipping cascade will actually take off. That's a huge uncertainty we need to work on. But it's possible if we go to 1.7 or 1.8, we could initiate the cascade. So an overshoot scenario carries actually considerable risk with it. So I'm going to conclude now with the bottom line of what this complex systems analysis actually says. First of all, I think we have marshaled enough evidence to say that this complex system framework is indeed plausible, and it poses very, very high risks. So I don't think it can be dismissed out of hand. As I just mentioned, there are likely to be far greater differences between the 1.5 and 2 degree Paris targets than just another 0.5 of a degree of warming. It could be the difference between not initiating that tipping cascade and initiating it. And the important point for this meeting is, under any plausible scenario that we can come up with, CDR technologies are not only necessary, but they are urgent. So what you've been talking about over the last 2 days is really, really important. And I think our analysis only verifies that we have to really get our teeth into CDR technologies, explore them much more often, and really start working on being able to use them just as soon as we possibly can. So let me stop there, and hopefully we'll have enough time for some questions and discussions. I know it's late, but usually this prompts a bit of discussion and questions. Thanks very much for your attention.
Thanks, Will, for a very sobering talk, I think, and just highlights the real importance of this meeting. And we will take some questions. So we have a question down here from Will Howard.
Will, I noted with interest you pointed to several geological analogs, the early Miocene and the mid-Pleistocene as two of them. We know the Earth warmed into the early Miocene, and yet obviously it did not run away into a hothouse Earth. Can we get any insights from that geological analog into the stabilizing feedbacks that prevented the Earth from running away in those times?
Okay, first of all, none of these are runaway scenarios, even our hothouse Earth. It just gets parked at a hotter condition, okay? So let's get this completely off the table. We'd never, ever say this is runaway. It's not. It's a complex system that moves from one state to another. Second point, mid-Miocene is a hothouse Earth. It's 4 to 5 degrees warmer, which is exactly what we're saying. And it was parked there for several million years. I didn't put the PETM up. They're called the Paleocene-Eocene thermal maximum, about 56 million years ago. That was a spike, again, of about 4 or 5 degrees temperature rise, probably from ocean methane hydrates, although we don't know for sure, and we don't know what triggered it. What we do know is it went 4 or 5 degrees warmer, and it took on order of 100,000 years to come back, and that's because of the stabilizing feedbacks, and they've been mentioned here, are silicate and carbonate weathering. The Earth system will bring these back down, but not in time frames that are useful for humans unless we accelerate them. Okay.
You mentioned the ocean overturning thermohalite circulation. Now, there's some suggestion that happened at the Permian Great Dying. So there's this, I suppose, risk of a mass extinction event at that sort of Permian scale, and that just seems to be a sort of like even if that were unlikely, it's such a primary security risk. I'm just wondering how you think about framing the language in terms of human security.
Yeah, that's really an important question, and the best way I can answer that is we do talk a lot regularly with the defense and security communities, not only in Australia, but in other countries around the world. And, a lot of people say, oh, this is really depressing. Why are you putting this out? This is terrible for communication and so on. Not with those communities. They really understand what risk is about. They want to know about this stuff. And they're the ones who can really start then saying, all right, if we start this tipping cascade, here's what we think the outcomes are going to be. And long before you see the direct impacts of this on people, you're going to see conflict, you're going to see security issues and all this sort of thing that I'm not an expert in, but people who are say that long before you see the direct impacts of what this hothouse Earth trajectory may take us, you're going to see all sorts of indirect impacts that are triggered in various places of the world and so on. So yes, those sort of things are thought about in the security defense community, including those really dangerous scenarios of really rapid change, ocean circulation flipping, all that sort of thing.
Yeah, I just want to address the issue of carrying capacity. So you cited a figure of 1 billion, and I think that the current UN projection for peak population is 10, so you're looking at an order of magnitude reduction of population in the human race, which is obviously, defining that as anything other than catastrophic is quite difficult, isn't it? So how well constrained is that figure? And a kind of a corollary to that question is about the island of stability that you were talking about, this engineered stability. I don't see any kind of engineering limits to our ability to tug ourselves out of the pit of the hothouse with SRM. So is there a fundamental limit to our ability? If we get over, say, 2.5 or 3 degrees, in your view, is there just no way back, or or can we just drag ourselves out of a pit of any depth? I know David Keith thinks we can snowball the Earth if we want to. He may or may not be right.
Yeah, okay, two questions there. First one, the 1 billion was an estimate by John Schellenhuber from PIC based on a lot of research that he'd seen. I don't think it's well constrained. I think you could come up with other plausible estimates that are quite different from that. The point being that it's going to be really hard to keep 7.5 or 10 billion people going with changes this rapid going on. And the other question, can we get out of this when we decide it's too much? Probably not, and that's where a lot of the uncertainty in our analysis comes in. We think that if the tipping cascade, we think we're pretty safe to 1.5. We're going to tip some tipping elements at 1.5, but we don't think we may tip all the dominoes. And in that case, you can pull back from 1.5 using a lot of what we're talking about here, or stabilize at 1.5 more appropriately. Somewhere between 2 and 3, I would be very hesitant to say we're safe. I think the risks go up quite sharply. And of course, the NDCs are putting us close to 3, last I saw them. And there we think once you get those dominoes, that whole cascade going, you're not going to pull it back with CDR or anything else. The Earth system just will have such strong intrinsic feedbacks. And that hothouse Earth is actually a very stable condition. If you remove all the northern hemisphere ice and much of the southern hemisphere ice, you are removing the major mechanism that moves it between glacial and interglacial states. And it can sit very happily at that state for quite a long time.
Right, just in the interest of time,
Yeah.
I'd like to thank Will.
Okay.
Thank you.